Okay, thank you, and well done. I think that was Mr. Karinungan. No? Okay, so is this clear for everyone? Are there any questions, concerns, or clarification so far? Okay, so we will proceed with our last topic now, but this is a rather easy one, no? Because we've done the Jacobi iteration. This is just some sort of a modification, no, of that process. So this is called the Gauss-Seidel method, attributed to Carl Gauss and Philip Seidel. Both are German mathematicians who made the contribution, no, for these iterative approaches. This is otherwise termed as the method of successive displacement, where the new calculated values of the unknowns are used immediately within that same iteration. So the requirements are the same for the as that of the Jacobi iteration, and that the assumptions are the same. No, that we have to have some unique solutions for the system of linear equations that we're working with, and we have no zeros in the main diagonal. So in the later example, we'll work in the same um, problem, but here we will highlight that in the steps 6 and so on. We can see the variation, no, of the Gauss Seidel versus that of the Jacobi iteration. That here we substitute the value of y0 and z0 from step 5 in the first equation to calculate the new value of x1. So same thing, no, up to this point. But starting here, we will use instead the new value x sub 1 to solve for z0, and I guess there should be y0, no? So might be some typo here, but this should be uh, right. Yeah, so use x sub 1, z0, and y0 in the second equation obtained from step 4 to calculate the new value of y sub 1. Similarly, we will use uh, x sub 1 and y sub 1 to find the new solution of z sub 1 and so on. Okay, so I guess we will proceed with the example later, no, to further demonstrate this. But the thing is to summarize the key differences, no, between the Jacobi iteration. In the Jacobi iteration, we solve for x sub 1 based on the equation 1, using the guesses, initial guesses for x sub 2 and x sub 3. For x sub 2, we use the equation 2 with the initial guesses for x sub 1 and x sub 3. For x sub 3, we use equation 3 from the initial guess of x sub 1 and x sub 2. And then these three values will be used for solving the new values of x sub 1, x sub 2, and x sub 3 in the next iteration. So the key difference is that in the Gauss-Seidel method, after obtaining the new value of x sub 1, we immediately use this and plug this into the equation to obtain x sub 2. So kind of the same thing for x sub 3, we immediately use the values of x sub 1 and x sub 2 obtained within that same iteration. So we can predict that using the Gauss-Seidel approach, the convergence rates are more rapidly obtained. No? Okay, so before we proceed with the implementation. So let's just cover some review questions. So that is kind of the same questions will appear in your midterm exams. No? So please consider these following questions. No? So which of the following is an iterative method based on the discussion? The Gauss-Seidel method is the iterative one. So it uses the Gauss elimination is based on the elimination of unknowns. Thus, it is not an iterative method. While the Gauss-Jordan is based on the back substitution as well as elimination. Factorization is based on the formation of two triangular matrices with the matrix from lower and upper triangular matrices. Okay, so for the next question, your turn. Gauss-Seidel method is also termed as the method of which of the following. So you can post your answers in the chat box based on the previous slides. Any answers so far? So what is the other term for the Gauss-Seidel method based on the previous slides? All right, so I suppose everyone is paying attention. Thank you. And the Gauss-Seidel method is also termed as the successive displacement. No? And that is because with the iterations, we keep on displacing the values we select for the unknowns which are used in the subsequent steps. Okay, so which of the following is an assumption of the Jacobi's method? Is it that the coefficient matrix has zeros in its main diagonal, or the coefficient matrix has no zeros in the main diagonal? Is it that the rate of convergence is quite slow compared with the other methods, or is it that the iteration involved in Jacobi's method converges? Okay, so which of the following is an assumption of Jacobi's method? And you guys are correct, no? So the coefficient matrix has no zeros in its main diagonal. So because we have to uh, divide, no, using the values from the diagonal. And that this is because the method employed for solving such a matrix that for every row the magnitude of the diagonal entry in the row is larger than or equal to the sum of the magnitudes of all the other entries, no, in that row. So this helps in ensuring that we have a rapid convergence rates if we have a large enough values in the diagonal, or we have a diagonally dominant matrix. And what is the other name for Jacobi's method? Is it the simultaneous method, the diagonal method, the displacement method, or the simultaneous displacement method? Right. So, and again, you guys are correct. That's the simultaneous displacement method. So, I guess this is the last question. What is the main difference between the Jacobi's and the Gauss-Seidel method? Is it the computations in Jacobi's method can be done in parallel but not in the Gauss-Seidel? Is it that the convergence in Jacobi's method is faster, or is it that the Gauss-Seidel method can solve the system of linear equations in three variables, whereas the Jacobi cannot? Or is it that the deviation from the correct answer is more in the case of the Gauss-Seidel method? Okay, please post your answers in the chat box. Right? So the main difference is that the computations in Jacobi's can be done in parallel but not in Gauss-Seidel. So you guys are correct, no? Because in Jacobi's method, the intercept of values obtained during the previous iteration is used as it is in the next one, whereas in the Gauss-Seidel method, As we keep on getting the individual values of the variable, we use them in the subsequent steps. Okay, so we can do parallel execution of each equations for the Gauss, but if we do it in sequence, then we can obtain faster convergence rates in the Gauss Seidel method. Okay, so any questions so far? Okay, so let's proceed with our example or the last exercise. No? Okay, so here is the implementation of the Gauss-Seidel method. So if you're done with the Jacobi iteration, here is the same problem. The accuracy calculations are the same, and in this particular example, we've used the same assumption or initial assumption of having zero values for all the x figures x1, x2, and x3. Now, in the first iteration, you can see here the key difference. No, uh, x1 is the same. You'll be using the previous x2 and x3 values, but for x sub 2, now you can see the improvement here that you will be using the previous x3, but you can immediately uh, utilize the x1 value within that same iteration. No? And similarly, for the x3 calculation, you can immediately use the x sub 1 and x sub 2 within that same iteration. And then you just have to repeat the process afterwards. Okay, so if you have the template for Jacobi iteration, then you can just copy that tab and do some tweaking. For your last exercise today, please work on the same problem and share with us how many iterations does it require to reach error rates below 1%. So same problem, no? But you will be using instead the method of the Gauss-Seidel here. Okay, so I'll try to highlight this one. No? So you can see the difference, no? In the case of the Gauss-Seidel and that of Jacobi iteration. So if you have any questions or concerns, you can uh, give me a heads up, or you can post your questions in the chat box.